go. So we have some of the confidence interval hypothesis test procedures, and so there's a kind of formula for each of those. There's a lot of stuff in the book. It gives some extra variation. But I could probably I'll list more specifically how we've done things, how it's in class, and kind of what to focus on, so that it makes it more manageable for the time. Yep. But yeah, that's on. We have the exam on Wednesday, so in a week. So Monday will be a review day. We're, I think, just a little bit ahead of what was kind of scheduled. So we're doing well in terms of covering material. It gives us a little more time to do some review, look at contrasting different types of problems, maybe a few related, tidbits here and there. But we have time to kind of try and synthesize these big ideas, because even though in the world of statistics you go out and do totally different tests and totally different procedures, a lot of the same rationale is still. Okay, so looks like it's about time to go. Right, so today we're going to look at two samples, two independent samples and inference for means. This is in chapter 9.2 of the book. The handout has 8.4 on there. That's from a different book, so I forgot to change that part of it. So you might want to just cross out the 8.4, 8.5, and write in 9.2, because that's where you're going to find the comparable material here. So the idea in this run is that we have two independent samples, two groups, treatment and control group. They're not matched individuals. It's two aggregates, or two groups that exist in society. Here we go. And we're comparing them. So in group one, we have a sample size in one, and in this we have a bunch of measurements. We're going to do the average of those. We're going to have a standard deviation of those in group number two. We're going to have another sample size, x bar 2, and SN2 is sample standard deviations. The values we're interested in, the parameters we're interested in are the averages of the two groups. And we want to do something to compare them. So we are either going to do a confidence interval for the difference of the two groups. And depending on your context, which is group one, which is group two, which you subtract from the other, becomes a matter of interpretation, right? So it's positive for one way. If you flip the definition of the group, it's going to be negative, and it just depending on the context of what you're looking at. So we could do that, or we could do a hypothesis test for comparing them. The most common hypothesis test, right, is that they're equal, which implies that the difference is 0, and the alternative is just two-sided if they're not equal. The other complication that makes this one, we'll have slightly different formulas for the difference in means and then the variances. The one little wrinkle is we have two standard deviations here. So there are two population values, these are population values. Two standard deviations there in the population, and are these the same or not? Right? If they're the same, then really this standard deviation and this standard deviation are estimating the same things. So we get some advantage by using one estimate of standard deviations instead of two. Instead of having two things that are variable and unknown, we only have one, we can use more data on it. And that's called the pooled procedures when they're the same, and we can combine samples for that purpose, right? So let's talk about how we would do that with pooled first. If sigma 1 equals sigma 2, same standard deviation. So the thing to do is to give a pooled estimate of variance. Right? So we have the first one, and we have the second one, the two standard deviations squared. If both of those things are estimating the same thing, we'd like to put them together. Sample sizes might be unequal, so we weight it by the degrees of freedom. So n1 minus 1 plus n2 minus 1 times that one, and n1 plus n2 minus 2 in the bottom. We get a pooled average of those standard deviations. And so this S, the pooled one, is the square root of this thing squared. And we'll use that as a standard deviation. The estimate of our difference is pretty straightforward. We have a sample in group 1 and a sample in group 2. This is going to be x bar 1 minus x bar 2. So that won't be exactly 0 in almost all cases, right? So the question is, how far is it from 0 relative to the variability we naturally have? So what's the standard error of this? There you go. So this touches back on the linear combination. So the question we're going to answer, what is the standard error of that thing? So the variance of x bar 1 minus x bar 2, one way to write it is the variance of x bar 1 plus the variance of x bar 2 minus 2 times the covariance of these things. That's the general formula. But if we have two independent samples, right, they're not matched, they're not correlated. Then the covariance is just 0. And that goes away. The variance of an average should be the first variance over n1 in the second group, the variance over n2. And if sigma 1 and sigma 2 are the same, some common value sigma, then this variance, if we put sigma squared in here, we can factor out the 1 over n1 plus 1 over n2, and we get that simplified version of the variance of our estimator. So if it's some common value, if they're equal, right? So in practice, we're going to put in that s squared, the pool, the sample version of the average of those two things. Right? For our estimate of that variance, the variance of x bar 1 minus x bar 2, we're going to estimate it, we'll put a little hat on it for the estimate, as this pool we're going to put that pooled version of those two standard deviations, two variances in there. Right? And that's what we use as the basis of our standard error. That's actually the standard error squared for our x bar 1, x bar 2.
So it's the variance of x, so that's 1 minus x2, right?
Yep.
Okay.
It would be the same formula. You know, if we took x2 bar minus x1 bar, right? They both you add the variances. There's no covariance, and so it's the same equivalent form. Whether you call it 1 or 2, that hasn't changed. The variance of x bar 1 minus x bar 2 is the same as the variance of x bar 2 minus x bar 1. It doesn't matter if you reverse them. So with all that, right, we're going to, so a confidence, so let's say a 95% confidence interval for the difference in these two things X bar 1 minus X bar 2. We use a t distribution because we're estimating the standard deviation. We're estimating that standard error based on the sample. The 0.025 thing, we have some degrees of freedom we have to use in there. And then we need the standard error. So that S to P, the square root of 1 over n1 plus 1 over n2. And that ends up being our standard error. The degrees of freedom we get to use turns out to be, in this pooled case, n1 plus n2 minus 2. Right? Like n1 minus 1, right? So 1 less because we're estimating the first mean. And then n2 minus 1 for the second group. And if they're the same, it works out that that is the degrees of freedom, so we get to add them together. So if either sample's large, we get a pretty large degrees of freedom. So let's look at a numerical example. Any questions? So, if we're measuring what's called vital capacity, vital lung capacity, you can take measurements of how much volume of air and pressure you can fail by hooking people up to machines where they take a deep breath and breathe. Right? Let's say you have some people who play brass instruments. We have N of those, and we have some people who are on controls. Maybe the same, similar ratio of male-female. Of course, you can't be exactly the same. Maybe age ranges are similar, but something similar without. Or maybe they're all non-smokers. They're all similar. No lung problems, or they're not currently sick, right? So that there's kind of a fair comparison otherwise. And the average vital capacity is 4.83 in this group, 4.74 in this group. Standard deviation in the first group, 0.435, and a standard deviation in this group, 0.351. Right. And let's say we want to do a 95% confidence interval for the difference. In average vital lung capacity. Sometimes this measurement is called FEV, or forced expiratory volume of the air that can come out. And these would be measures in liters, I believe, of air that would fill up. So if you see one of these types of problems on an exam, right, you have two independent groups, you need two sample sizes, two averages, two standard deviations. So that whole structure has to be set up there. Right? And then it's comparing the averages in the groups. So our estimate, X bar 1 minus X bar 2, 4.83 minus 4.74, does not look, right, if this is like liters of air, right, does not look like a whole big difference. Now, of course, a small difference on any scale, if you have big enough sample sizes, small enough standard deviations, might still be a significant difference. Statistically significant to be different than the practical significance of things. So, we would want to look at it. This is a pretty small sample, I suppose. So maybe this is kind of a pilot study for doing larger studies of things like that. To do this, we need to do a few steps. Degrees of freedom we can figure out, right? N1 plus N2 minus 2. In this case, it's 13. So we have that t-value. I don't have exactly that t-value. Let's see if I can locate that T-table. Rosner, there's our T-table in the recent things. So with 13 degrees of freedom, right, and the 0.025 looks like it's 2.16. Right, it's going to be our T value. That's on there.
Where did you get the 0.205? Oh, never mind. That's their alpha. Gotcha.
That's related to the alpha, exactly.
Yes.
Yeah.
Sorry.
Yeah.
I just
And doing a
Like,
two-sided
second.
test, 95% confidence interval, at least 5% over, we can half of it. So 2.16 for that. So the T value, 0.025 with 13 is 2.10. But we need that pooled version of the standard deviation. These two are not exactly the same, they're pretty close. Usually it's reasonable to pool if they're within kind of a factor of 2 of each other, right? And so if we take S1 squared into minus 1 plus S2 squared into minus 1, A1 into minus 2. Folding paper, so we did 7 times the 0.435 squared plus 6, because there's only 7 in that group, 0.351 squared. And then over 13, kind of that average of things. So we have to do that. The pooled one ends up being, well, 0.1628 squared. Oops. No. Ends up being the square root of 0.12. I said it the wrong way. Square root of that. Right. So you calculate all this, you get 0.1628, but we want to do the square root of that. And so the standard error that we want to use, you do the square root of that thing. And then there's 1 over 8 and 1 over 7. Our standard error, I did write down, ends up being about 0.236. You put all those numbers in there. So our confidence interval, put all this stuff together, right, the average
So is
difference.
that multiplied by 1 over 8 plus 1 over 7?
Yeah, this is the, it's 0.1628 times 1 over 8 plus 1 over 7, and then just the square root of that whole thing.
Okay, I see.
Be another way of writing it. So our confidence interval for the whole thing, x bar 1 minus x bar 2 plus or minus our t value times the standard error. Right, so just only 0.09, 2.160, our standard error, we count as 0.236. This is an interval. That's going to include 0. It's really going to be plus or minus straddle 0 pretty strongly. Get R started. So that's small too, right? So if we want 0.09 plus, or plus the 2.16 times the 2.236, that's the upper one, or minus that is down there. So negative 0.42 up to about 60. I think it's in liters of measurement of error. Right? That would be the 95% confidence. Right? Do these groups look different? No, not really, right? That includes 0. There's a a little bit, the estimate is a little bit different from zero, but relative to standard error, it's not very different. So, yeah, it's a small sample size. Maybe bigger sample sizes, this would persist, or, yes?
Right, so how would you tell then from this whether your initial, like, with your initial value from the subtraction is significant versus not? Because we just did the 95% interval, but like how would you be like, well, or could you ask if we're doing it this way?
Right,
Of like,
this
is that
a 95
significant?
confidence interval for the difference. Right. The way to do a hypothesis test, whether these things are equal or not. If they're equal, that means that the difference, right, is zero, versus just an alternative that they're not equal to zero. But t statistic for doing this test is going to be our estimate minus zero, technically. We subtract the null value. You could test, is there a fixed difference, if that was of interest for some reason, over standard error. The estimate, the distance from to the null hypothesis divided by the standard error of x bar 1. So this is 0.09, this is the 0.236, and so that gives a t statistic of about a quarter, and about 0.25. And a more extreme value of a t statistic with our 13 degrees of freedom. If we're doing a two-sided 5% test, and we look at that value was 2.16, 0.025 standard errors. It's not very many. It's not far away at all. Right? Because this is closer to zero, we do not reject.
Okay, thank you.
Yep. But to further follow on that, you could tell from the confidence interval that you're not going to reject zero. Zero is right there in the middle of the confidence interval. And if it's covered by the confidence interval at all, you're not going to reject. So 95% confidence, alpha equal 0.05 level. So if this is your testing standard, so you would look at 2.16 here. The 2.16 here also ends up in multiplying the standard errors. So you don't reject. Right, so if it's not, so we could, right, if it's not pooled, now for most things, I think it makes sense to pool, right? That if they're not more than a couple, orders of magnitude apart, that there's some advantage to pooling these together. Right. You get to use that degrees of freedom as an exact solution. If you're testing about the means and the standard deviation happens and the whole distribution end up being quite different anyway, there might be other things you're looking at. Right? But if it's not pooled, right, the variance of x bar 1 minus x bar 2 was this sigma 1 squared over n1 plus sigma 2 squared over n2. The estimate that we would use for that if they are not equal, well, we have the sample standard deviation or sample variance from each sample by itself. All right, so we would just use s1 squared over n1 plus s2 squared over n2. That's all fine. That's not hard to do. From the point of view of probability theory and distributions, the distribution of the t statistic, when you take x bar 1 minus x bar 2 over that, when they're unequal, so before we replaced each of these by the pooled ones, so we could pull it out. It becomes a little simplified. From the point of view of statistical theory, this is a classic problem that the distribution of that exactly is not quite known. most people in applied work don't care about that particularly, but what it's going to mean is that the degrees of freedom that we use for comparison, it's not perfectly known what to do. There are different ways that you can approach this. One way is conservative. The degrees of freedom is you make the smaller of these two individual degrees of freedom, and then you won't make too much of a type 1 error. You won't make confidence intervals that are too short. You won't reject things too often, and you should at least get 95% coverage, if not more, for 95% intervals. And your type 1 error, your 5% significance, should really be at least 5% significance, if not even a little bit better, lower error rates.
So when you're saying this, you mean that we go with whichever has the smaller n value and go use that to determine the degrees of freedom?
Yeah.
Okay.
An alternative to this, being really conservative that way, is that there's more complicated approximations. Things called approximations to the degrees of freedom. There's a statistician from the Satterth. Always hard to remember how to spell Satterth. I have one H somewhere too many. But there's an approximation to it that's more complex. That gets used in practice. And you can compute that, but it involves a few different terms and things. But it's going to give you a number, right, as degrees of freedom. And we can compare the t statistic to a t distribution with those degrees of freedom. If we want 5% significance or do a 95% confidence interval, we're going to use that number there. So it makes, often it makes a little bit of difference in that. So let's look at what we get. So in this small example with the brass players, the values that went into that 4.7, 4.6, 4.3, 4.5, 5.5, 4.9, and 5.3, the mean of those is 4.83. The standard deviations of those is this 0.435 rounded up. The control individuals had these values of, they're at 4.7. I believe that's a 4. That must be like maybe 4.2, 4.3. Let's see if this works out. 5.1, 4.7, and 4.7 is 5.0. That's the mean of the control. 4.8, 4.76. Maybe this is a 2. Right there. So the mean of those 4.74. That matches what I told you. And the standard deviation, that matches what I told you. And so in R, there's this t-test procedure. If you give it two things, brass and control, for those two vectors, it does a t-test. It calls its t-test is Welch. That's the degrees of freedom approximation it's using. Satterthwaite, Welch, there's different names that go with these things. And see, it's come up with, if we had 8 in one and 7 in the other, the conservative thing is 6. But if we had pooled, we'd have 13. And so this says actually, well, the kind of the compromise when they're unequal is 9.76. It can calculate cutoff values and p-values and all that stuff for these fractions. So it comes up with the degrees of freedom that's some compromise between that. A t-statistic, when these things are not pooled, is a little bit larger, but not very extreme. The p-value 0.705 is a lot bigger than 5%, so we wouldn't reject. These things are not different. The confidence interval, look, so those are the means. Here's the confidence interval. Looks very similar to what we had before, but it's a little bit different. Right? So it does this, I think maybe there's the help file for this, the student's t-test, for the two-sample test. If you want to call the variables equal, you can have an option that tells them pool it, use equal variances. Let's see, but let's see. If it does give any more, it doesn't give any more details of what it's doing there in terms of the test. But if you do tell it to var.equal as an option, if you tell it it's true or just t, it will pool it. And see, it's done degrees of freedom here as 10. Let's see, why is it only 10? Did I get everybody in there? The length of brass, oops, is only 7. Am I missing somebody? And the length of control is only 5. So I don't know why I only have this. This seems to be, not all the numbers are written down here. Interesting. So anyway, the data that I put in only had 12. So 7 plus 5 is 12, minus 2 is 10. So it's not pooled, it's here as 10. Interesting. And, so if you do control it, it says you're doing a two-sample test. It's pooled the things together. Yes.
Is there like a certain kind of like research experiment where like doing a pool test would like give you more accurate results than like another?
Right. So what happens if you're able to pool these things together? Right. So pool, right, versus don't pool. If you pool, you have your S1 squared and S2 squared from your two samples, but they get combined in this pooled one. So you only have one estimate instead of two. If you don't pool, you have the two separate things. Right? So in one sense, you're estimating one fewer thing, so your data can make a better estimate about that. Maybe in one of these samples, S1 squared or S2 squared could be kind of unusually extreme, and you have more chance of kind of an odd thing going on. So generally, this should be a superior estimate if the variances really are the same. It's better to use both of them for one thing versus two separate things. In terms of degrees of freedom, if this one uses n1 plus n2 minus 2, and this one either uses the smaller of the two things here or an approximation. The approximation degree of freedom is just going to be smaller than that one. So this is the bigger degrees of freedom. What happens if you have bigger degrees of freedom? What are the consequences of that? If you have bigger degrees of freedom, what happens to our t-table? As degrees of freedom get bigger,
More variance. Where like the intervals are.
yeah, so say under one of these columns like 0.025, what happens to these cutoff values as we get more degrees of freedom? They get smaller, right? If we're able to put together two samples to get bigger degrees of freedom, our multiplier for our confidence intervals is smaller. We get narrower confidence intervals if we're willing to pool, right? So our t, like our 0.025 degrees of freedom value over here is smaller. And over here is bigger. So if other things being equal, that this one gets a smaller, so x bar 1 minus x bar 2 is going to be the same in both cases. We have some t value, plus or minus a value there, and then a standard error, right? We get a narrower intervals if that value is smaller. Narrower intervals with smaller t critical value in there. And if we're looking at hypothesis testing, right, the x bar 1 minus x bar 2 over the standard error, you're going to judge is it extreme or not, right? And if you're comparing it to a smaller t cutoff value, there's a better chance for significance, right? So there's some advantages to pooling. By getting a better estimate, I think, of the standard of this common variance, and then it shows up in that degrees of freedom for t, and it does a little bit better. All right, so let's look at one more. But any questions? So usually, it's like to pool, but if those look vastly different, you kind of underlying this is a model. It essentially says that the pooling says that the model says there's really a common variance, the same in both groups. And if one group's really more different than the other one, that would kind of present a little logical problem. It might be a little inconsistent. When would that show up, particularly? You have real small sample sizes, and one of the groups has some big outliers, right? That's going to set things haywire. It's going to affect the means, affect the standard deviations. But if you have a real small sample sizes and big outliers, the test might not be that reliable anyway. So you want to look at the data, check the standard deviations, look at the plots. Does one group have massive outliers and the other one doesn't? That's going to affect your interpretation of things a little bit.
Can you be kind of suspicious that they have a very small sample size to begin with anyway?
Yeah, so I usually think of that's probably mostly appropriate for pilot studies, small things. But I published some papers, applied work that had small sample sizes. When I was at George Washington University, some colleagues there worked with children that had speech or cochlear ear implants. Right? And so they had some speech impediments and difficulty recognizing some parts of speech. These were children 2, 3, 4 years old. And so for them, they show them 3 pictures, and then somebody says a word, and they ask, the idea is the children are supposed to identify what they're saying. And if it's 2 words that sound similar but have kind of like dog versus pig, well, maybe they have better examples, right? So it has kind of a similar aspects of speech, dog versus, I don't know what example, I can't think of it. Hog, something like that, right? Yeah, if they're supposed to be able to identify it based on the sound and point at it, children at that age that have normal hearing capacity can get excellent scores. But different children with implants have different aspects of speech that work for them, and they can learn and things, but identifying it like that. And so that's expensive. Bring in children, their parents, you set up a laboratory, you video record the interaction so you can get a lot of data and make sure you're not missing something happening in real time. And there you might have 10 or 15 in each group, and that's it, right? You measure them each for an hour of activities, and it's hard to get much past that. Right? So sometimes a lot of valuable studies are done based on small groups. And if there's a strong signal, there's a real big difference between the groups. X bar 1 combined with X bar 2 is big enough, and there's still a significant effect. Right? But in many other things, larger ones are usually at larger sample sizes. So tonsillectomies, right, can be used for surgery to remove the tonsils, maybe the adenoids. Right? And there's conventional ways of doing it. But there's another surgical technique called coblation that does things a little bit differently to reduce pain, more cauterization. I don't know all the details, but an experiment randomized individuals to 2 different groups. There were 47 who received conventional treatment, 52 with this new surgery procedure. And they're measuring pain on a scale. The average reported value of pain is 4.3 for this group, 1.9 for this group. So the difference in the samples ends up being 2.4. The standard deviation in the two groups ends up being 2.8 and 1.8. If you pool these things according to our formula, we get 2.33. The pooled standard deviation is going to be somewhere between the two ones for the group. It's a weighted average of the variances. So somewhere between, not exactly in between, right? Because it's based on degrees of freedom and it's on the variance scale, so but it's somewhere in between. The standard errors, you did each group individually, 2.8 over the square root of 47 is 0.40. Right? And this one, 1.8 over the square root of 2 is 0.25. And you can say compare the two groups. Is this coablation method of surgery, does it lead to a significant reduction in pain, right, from this type of surgery? Do you want to do confidence intervals? Do you want to do hypothesis tests? Do you want to do pooled or not pooled?
Can we do pool just to make it easier on ourselves?
Okay. Well, so
I know that shouldn't be our reasoning, but like.
Yeah, I think, even though the standard deviations are a little bit different, they're not grossly different. I would probably, my first thought would be to pool them. Look at the data. If this is on a 10-point scale, that there's probably not going to be that big of outliers because the scale is from 0 to 100. Then maybe you get some outliers in there. But if it's 0 to 10, it's not going to be sticking too far out. So I wouldn't be overly worried about it. So we do a confidence interval for average difference. Alright, so x bar 1 minus x bar 2 plus or minus a t-value. And if we pool, then it's 1 over n1 and 1 over n2 in the two samples times the standard deviation there. So the difference is 2.4 on the 10-point scale. We need degrees of freedom. So for pooling, n1 plus n2 minus 2. So we had 47, 2, 47, 47 plus 52 minus 2 is 97 degrees of freedom. If we do 95% confidence intervals, we'll look in the 0.025 column. And 97 is not exactly there, right, but 97 is going to be between those two places, 60 to, so 1.99, 97 somewhere in there. Based on the accuracy that we're doing stuff. 1.99, and then the pooled, I told you was 2.33. We have the square root, 1 over 52 plus 1 over 47. And it is 1.47 versus 3.33. So that's a 95% confidence interval for the difference in average pain scores from these two procedures. So which one do you want to use?
The new method?
The new method had the lower pain scores, it's a conventional minus coblation. You get this reduction in pain. All right, so I guess you would write that this is a 95% confidence interval for the amount of reduction in average pain, based on how I phrase it. And that seems, if it's a 10-point scale, that seems pretty good, right? So it probably is worth training surgeons, right? Going forward to medical schools to consider this if they're going to be doing that operation. Train colleagues that are already there, train new people to do it, and then justify that recommendation.
All right, so we know that it has a significant reduction in pain because 0 is not within the
Right.
confidence interval?
Right. Yep. If we did a hypothesis test.
Would we have to do both for, just to prove that's significant, or could we just do one or the other?
Either one would be convincing.
Okay.
If we wrote a research article and you gave the confidence intervals, 95% confidence interval, so that you say that it's clearly not zero, it's statistically significant from zero because the confidence interval doesn't include that. Sometimes articles could give the confidence interval. We actually wanted to see the reduction in pain scores and maybe a p-value. You could put both in there. It's a little redundant, but it's all about communication and about communication and how do you portray the results. Showing box plots side by side or a table. If everybody gave an integer 1 through 10, you could do tables or something that would show how the distributions are. One's kind of shifted down versus the other. You could illustrate it a few ways. But if we did the hypothesis test, we would take x bar 1 minus x bar 2 over the standard error. So it's that pooled 1 over n1 plus 1 over n2. In this case, the t statistic ends up being 5.12. Right?
Wow.
Yeah, well, it's several standard, the difference. Why is it so big? I guess I didn't compute this, but the 2.33 times this, 1 over 52, 1 over that, so it's like 1 over 25 almost, or yeah. And so that's like 1 over 5. So this is, the standard error is something like 0.5 or so. And the difference is 2.4, so it's 2.4 over 0.5. It's almost, it's a multiple of more than 5. So it's quite a bit way. The confidence interval wasn't really close to 0. Right? It didn't even come close to being on there. So that's why you get such a big t-statistic. It's overwhelmingly significant. Degrees of freedom, again, pooling, 52 plus 47 minus 2 is 97. And the cutoff for significance at the 0.05 level was 1.99. And so you rejected the hypothesis that they're equal because the t statistic is so much bigger than that cutoff value from the distribution. The p-value, in this case, if you calculated the probability you're greater than 5.12, is practically 0. Articles might hit a p-value less than 0.001, meaning highly statistically significant, 1 in 1,000 or more rare than that. Any questions about? So the handout has just a couple more examples to illustrate how this goes. Right, so in one, you have 36 dog owners. They asked them, how much do you walk per day? Now, it doesn't necessarily mean that they're only walking because they have the dogs. And they have cat owners that are walking some days. So this could be getting to and from work, to and from errands, and other things.
It could be walking the cat, possibly.
Possibly, right. Or chasing the cat around the house or something, right? Right. It doesn't say exactly how they monitor this, but pedometers are much better than they were 20 or 30 years ago, so it could have been some kind of active monitoring of what people are doing, right? And they have a standard deviation there of 1.7 miles for the dog owners or 1.5. The question is, do the dog owners walk more? Is there some type of benefit from doing that? Right? So it appears so, right? Because it's 4.2 versus 3.1, but it is statistically significant. So if you pool it, you're going to have to pool those there and get that. The pooled one is 1.62. It's between the 1.5 and 1.7, so you can do just kind of a little mental check that it's kind of in the right ballpark. For pooling, we can use the degrees of freedom of 62. And our cutoff value would be about 1.999, looking it up on the computer. So a confidence interval there would be the average difference, 1.10 plus or minus a standard error, about 0.8. And then you get that confidence interval, which would be significant. Again, this doesn't include 0, so there seems to be a significant difference right there. So how do you know this is not a matched pairs study?
The t-value is significantly bigger.
Well, so but by a matched pair study, I mean that that there's matched pairs where you really should take differences. So this is on Monday we looked at paired data where you would have our two measurements, but each one would be measured on a certain unit, right? And in that case, we took differences because the first and second measurement on a person. So so if this is neighbors or friends, or the person in the household who walks the dog, and the person in the house who does not walk the dog, so there's some commonality there. And down to individuals, so the difference, the difference was here. Right? So that was a matched pair. Sometimes it's called paired data. Sometimes it's called matched pairs. What clues you in that it's not matched pairs? Yeah. Yeah. So if there's not, in this setup, it has to be equal numbers. But let's say I had 36 dog owners and 36 cat owners. What if I had 36 and 36? How would you know? Part of it, yeah, just the description of the problem. You could have done a study with cat owners and dog owners, right, where it was matched pairs. You could have set something like that up, right? So in every apartment building, you could find a dog owner and a cat owner that lived in the same location, right? But one owned a cat and one owned a dog, right? And for those two people, you could have recorded mileage. The amount that you walk could depend on your geography, right? If you live near some trails, you're more likely to do walking. If you live in an environment that's just surrounded by traffic, maybe you're not as inclined to take long walks or something like that. Right?
Or maybe you are more likely because you don't want to drive your car.
Maybe, right. So if you can walk to work or something, and you get two people that both walk to work, and one owns a dog and one owns a cat, right? Then you can do that in matched pairs. And if there's a correlation, paired data can be more precise, right? Yeah, so you might think about those things. But the next one was about the amount of pounds of weight loss for people in different programs, some with a low-fat diet, some with a regular diet, but both with exercise programs. And over a period of time, the difference is there, and so you get two averages, two standard deviations. Even though the sample sizes are the same, if the description of the problem says they're randomized to these two groups, right, then it's two independent samples, and you would do this instead of a paired example. But any questions about it? So that's about what we have to do in terms of comparing a couple samples. Right? And we'll come back on Friday. We'll have more information about what to study for the exam, which are the formulas out of the book and so on. The homework due, a couple of the problems are on this type of example, very kind of application oriented. Yep.
Present? I have a little quick story, and then be able to get homework 7 done by the end of this day, hopefully. Yeah.
That's it. That one I went
It's an exam Monday.
That's it.
Wednesday.
It looks different, yeah.
So we'll talk about more about the exam on Friday, including formula sheets and things like that. And, review on Monday, review problems, no problem, do that week. This week.
The next big thing is the project, right?
Uh-huh, we'll talk about the project right after that.
The final project.
That's just the project. Yep, the project, the final exam.
So I'm getting close to
I don't know
the
if
details,
it's
you know?
further yet. Then we're
April 29.
I think we talked about it.
Yep,
All
yep,
I'm
yep.
doing now, just a little more.
Yeah.
Talk about it. I'm probably gonna let you on it, so.
Thanks for bringing it up now.
Yeah, well, I kind of make sure
At
I
least I
set
have
my
to go
stuff
home.
out and do it early as well.
This class, because otherwise that would have
Tomorrow,
been
talk about
more
it.
than 12 hours.
Yeah, let's talk
without
about it.
going home.
We could meet
I'm available all day.
tomorrow, so I have class
I did that last semester
8,
a lot.
or, you know,
Yeah,
in the
I
morning.
remember you being-
So afternoon is a little bit better.
Last semester, I had
Let me write, I think I have something right then, somebody wanted to come by, so
9:45.
I already have one appointment then, but we
1
can meet.
o'clock?
Yeah, something like 1 o'clock.
Okay.
and then I had lab.
Yes.
Looking ahead, I know I already missed or
Then I had
Monday, but
lab,
I'll
then I
be
had senior stat.
away at the last
Then I
race
had
on
tutoring.
Wednesday,
Lab.
Thursday.
This-
Next week.
I did
Uh-huh.
have like a break.
And so we have
today
our
for between like 10 and 15
exam
when my lab started.
then.
Wasn't really enough time.
So Wednesday, Thursday, and
Yeah.
Friday, 5.
Yep, I'll be in, or I won't even be on campus.
Right. So,
Then that's it. I'm done for the year.
ah,
Yeah.
same, so I'll meet him at 1 p.m. Thursday. He's leaving for the military, 29. 1 week before the end of the semester.
Yeah.
So that's tough. And then you'll be gone. Yeah, all right, Wednesday, Thursday, Friday, next week. So, right, so the exam is scheduled for Wednesday.
My coach will be there. He has proctored exams in the
Okay.
past. I don't know if you're comfortable with proctoring exams or.
Yeah, no, that's, we can work out with the coach.
Okay.
And, you know, whether it's done on Wednesday or done on Thursday, everything
At
could be
some
available
point
at
during
some
the trip,
point
yeah.
during the time. And then if you could send it back to me somehow.
Like email or
If you
some.
can scan it, or,
Okay.
you know, I don't know if he'll be back on campus to drop it off, or he
He-
probably won't, or.
I don't know. They don't know what the plan is yet because everybody has different schedules. Like some people are only doing like Thursday, Friday. Some people are
Right.
only doing Wednesday
Right.
and Friday. And
Yeah.
so they might end up coming back and forth between campus, or at least the assistant coach might be
Right.
shuttling
Yeah.
people.
If you take it and they can drop it off then, but mostly just if they let me know.
Okay.
And then I can get it before the class on Monday. then
Yep.
that would be great. And so if they could send me an email saying we, you know, started the exam at this time
Right.
and you finished the exam and we have it, and
Okay.
so I know those details, but
Okay.
that'll work.
I'll send an email to my coach and I will
Yep.
CC you in the email.
Yeah, that'd be great. We
And
can set
then
it up.
we can start that.
Okay.
Thank you.
Hi, Yvette. How you doing? Oh, was there an email from that? I'll have to, I'll look through my notes. It might be further down in my, if I didn't file it in the right place, then it might be further down. But I didn't see the paper, but I will look for the email. And if I don't see it, then I'll write you. If you could send it again, then I can look at it, so. Okay. They missed an assignment or something, yeah, so. Okay.
I sent
So-
to them, but
They didn't send, yeah. Every once in a while, so, you know, you think you send it, but if somehow it's not connected to the internet or data service, then it just kind of sits there. Sometimes if you go to like, for instance, Outlook, there might be a sent folder, and sometimes it will say inside of that there is a delivery error or something like that. But in any case, I'll look for it, and if you, you know, if it's convenient, you can just send it again just to make sure. I'm not sure I recall it exactly, so. maybe didn't get through, but I'll take a look at it and grade it if you send it to me. So. Okay, yeah, yeah. Recommendation for you for going on to graduate school in data science or statistics or data science, yeah. So I can write a recommendation, sure. So if you send me an email with the places you're applying, I can write a letter. Yeah, so, good. Yeah, I'd be glad to write a letter based on the different courses and your background. So. Okay, sure. Uh-huh. Okay.
How are you doing, Professor?
All right, good.
The early class get out early or?
A couple minutes.
Couple minutes.